Welcome back, engineers. On behalf of Forge College, I am super excited to have you here for another explainer. So in our last lesson, project scoping and data-types-solidity planning, we did all that grueling work, right? We conceptualized our data, picked out our basic primitive types, and really did a thorough site survey. But today we're stepping right into the drafting room. We're going to draw up the official patent-style blueprints for your smart contract code. Let's dive in and see exactly how we turn those raw concepts into highly optimized Solidity architecture.
Okay, here's our blueprint legend for this explainer. We're going to kick things off with the blueprint phase. Then we'll get into nesting smart structs, tackle the great debate of arrays versus mappings, break down memory versus storage, actually start drafting your code, and finally, make sure your contract inspection ready. Let's get to it.
Section 1. The blueprint phase, from concepts to concrete code.
So that initial site survey of picking out basic primitive types, that is completely in the rearview mirror. Now we're taking all of those meticulous design notes you made, the field type tables, the list of entities, and we're converting them into a real drafted set of actual Solidity declarations. This is literally where the rubber meets the road. Because think about it, this layout defines your contract's core storage. Nailing these architectural choices right now ensures that all the functions and tests you write down the line are going to work with predictable, rock-solid data shapes.
Moving right along to Section 2, nesting smart structs. Modular building blocks.
Now, writing out the exact same variables over and over for every single entity, well, it's kind of like building a high-performance sports car and then just slapping square wheels on it, right? It makes no sense. Instead, we use structs. In Solidity, a struct is basically a custom data type that lets you group several variables together. Picture it like a highly organized modular filing cabinet. So instead of having loose variables just flying everywhere, you're grouping related data neatly together. It makes your code infinitely more manageable.
Honestly, this right here is the difference between an amateur approach and a true professional engineering approach. A classic mistake we see a lot is developers duplicating fields like name or created at inside every single entity. That just wastes space, and worse, it wastes gas. The pro move here is what we call nested struct composition. You actually extract those common repeating fields into their own dedicated metadata struct and then just embed that inside your larger entities. It's super elegant, it absolutely saves on gas, and it centralizes any future changes you might need to make.
In fact, you might actually want to write this down and literally tape it to your monitor. Extract repeating patterns into nested structs to centralize field definitions and reduce duplication. This is an absolute golden rule of smart contract engineering. Anytime you see data patterns repeating, let that be a massive flashing sign telling you it's time to create a nested struct.
All right, Section 3, arrays versus mappings, wiring the contract.
Okay, so if structs are our building blocks, arrays and mappings are the actual wiring of our blueprint. Let's start with mappings. A mapping is a key-value data structure. Functionally speaking, think of it like a giant, heavy-duty switchboard. You plug in a key, and boom, it instantly connects you to the correct value. And the best part? This offers massive gas efficiency with O((1) lookups, which is really just a fancy computer science way of saying it costs the exact same super low amount of gas to find an item, whether your list has 10 things or 10 million things. That's pretty huge.
But wait, it is a constant battle of arrays versus mappings, and you really shouldn't just use mappings for absolutely everything. You'll want to use arrays when your list length is, relatively modest, and you actually plan on doing sequential iteration. But if your dataset is huge or items are constantly being added and removed, you absolutely have to use a mapping. Let me explain why. If you try to remove an item from right in the middle of a massive array, the contract has to shift all the other items over to fill the gap. That's an O((n) operation, meaning the gas cost just gets heavier and heavier with every single item in the list. In Solidity, that will cost a literal fortune, and your users are going to be crying over those transaction fees.
Consider this matrix right here to be your ultimate cheat sheet. These are the three main mapping patterns you're going to use. First up, the single record by ID pattern. This is where you map a unique integer ID to an item struct for lightning-fast lookups. Next, we have the one-to-many index. You'd map a user's address to an array of their item IDs, basically to enumerate everything they own. And finally, the many-to-many reverse lookup. Here you map a tag ID to an array of item IDs. You'll use this to find all items that share a specific tag. Seriously, keep these patterns handy as you draft your contract.
Section 4, memory versus storage, the staging area.
Now we are shifting gears into one of Solidity's trickiest, but honestly most vital concepts.
This is the critical difference between the permanent vault and the temporary workbench. When you define a variable using the storage keyword, you are creating a direct reference to the actual data sitting permanently in the blockchain vault. Any modifications you make will alter the state permanently. On the flip side, memory is basically your temporary workbench. It creates a temporary value copy that only exists for the duration of the function call, and then, poof, it gets completely wiped away.
Which naturally leads us to a very scary but honestly super common question. What happens if you accidentally copy a massive nested struct from the vault onto your temporary memory workbench just because you wanted to read a single tiny Boolean flag? Well, the answer is pure tragedy. You end up paying a ridiculous, astronomical amount of gas to copy a bunch of data you didn't even need to modify. So rule of thumb, always be incredibly deliberate about when you're using storage references versus temporary memory copies.
Moving on to Section 5, Drafting Your Code, the Assembly. All right, it's time to open up your project folders, whether you're using Remix, Hardhat, or Foundry, because we are starting the hands-on assembly right now. Here is your clear-cut drafting process. Step 1. Translate your conceptual entities into top-level structs, and make sure to extract any of those repeating patterns. Step 2. Choose your wiring. You need to definitively decide where you'll use arrays versus external mappings. Step 3. Go ahead and declare those primary storage mappings. And finally, Step 4. Add some small manipulation functions. And hey, I strongly encourage you to add brief comments justifying your gas trade-offs. Believe me, future you will definitely thank you for it.
Now, regarding that last step, Step 4, I really want you to write some tiny helper functions right now. Things like create item or add tag to item. Keep in mind, you're not writing full business logic here yet. You're writing these purely as diagnostic tools. It's just a way to verify that your memory and storage keywords are behaving exactly the way you intend them to before we get any further into the weeds.
Section 6. Contract Inspection Ready. The sign-off.
Okay, so the blueprints are drawn, the code is completely drafted, but before we jump into any heavy-duty testing, we definitely need a final inspection. Here is your critical sign-off checklist. First off, does your code actually compile locally without any type errors? Second, do your field types perfectly match the original choices we made in Lesson 1? Third, are your mutating functions strictly using storage references to avoid those tragic, expensive memory copies we talked about? And finally, is your mapping architecture consistent? If you see any compiler warnings, stop and correct them right now.
Once you successfully pass that inspection, what you're left with is your final artifact. You should now have your capstone data.solve file containing all your shiny new layouts, your helper functions to verify everything is working, and a short, written change log documenting any representation decisions you tweaked along the way. Make sure to keep this artifact highly organized, okay? It is the absolute required backbone for what we'll be tackling in the very next lesson.
And that leaves us with a pretty provocative thought as we wrap things up today. Will your freshly drafted blueprint actually withstand the rigorous stress tests of validation? Well, in our next explainer, Testing and Validation, we're going to subject this exact layout to comprehensive unit tests and automated checks to see if it truly holds up. That is all for today's explainer, engineers. On behalf of Forge College, I want to give a huge thank you for joining me to master advanced structs and mappings. To dive deeper into this subject and to master even more Web3 engineering topics, be sure to visit us at forge.college. Keep building, keep optimizing, and I will see you in the next one.